Section 12.2 is the next section, and everything we talked about up here in 12.1 still works, except for we're just going to now allow for 3 components. And in fact, all these ideas even work in higher dimensional spaces where maybe our vector list goes on for a long time. So notable difference here is our length would have another term plus the third component squared. In this section, the main thing that was talked about is how to parameterize a line in 3 dimensions. So in 3 dimensions, in order to write down a parameterization of a line, what we can think of here, as starting with, well, what do we know about 2 dimensions actually? In 2 dimensions, to write down the equation of a line, you need 2 things. You need a point on the line, and you need a slope. Okay? Well, as we move to 3D, we're going to need to have 2 things. We're going to need a position vector, and we're going to need a direction vector. Each of these things fulfill the same role as a point and a slope in 2D, but with higher dimensions, sometimes things need to change, and it just so happens that these are parameterizations, so they are vectors. So let's say we have a point right here. Okay, let's say the point P, and this point is x naught, y naught, z naught, just like the point in the description here. The position vector, the position vector, all its job is essentially, it's a vector that points from the origin to the point on your line that we're using. So in this case, we're using this point P, x naught, y naught, z naught. So this vector O to P is a vector that points from the origin to this point. So there's the vector O to P. So what we can do is we can think of the position vector as having a purpose, and its purpose is to move onto the line. So it goes from the origin and it just brings us to the line. Now that we're sitting on the line that we have yet to draw, we now want to think about this direction vector. The direction vector tells us the direction in which this line extends. Maybe it's this direction. Maybe that's the direction vector. Let's call this direction vector V. Okay, so what we could do here is imagine this vector being right there. So now, if we do following the principle of geometric vector addition tip-to-tail method from above, and described in the previous video, if we go from the origin and we add the vector O to P plus this red vector V, it's really as if we've got a vector from here to here. So imagine if we include that point on the line. Okay? Well, if we look at the actual parameterization, we're always going to take this point, this vector that points to the point on our line P, and then we're going to add to this vector some scalar multiple t. So here t is some real number. So t copies of v. So in this case here, I chose to add 1 copy of v. So this is like t equals 1. Well, what about t equals -1? Well, -1 would just add the same length as v. So take this vector here, but then rotate it by 180 degrees. That's what multiplication by negative numbers do. They flip. So for t equals -1, we would do O to P minus 1 times v, and we'd include this point on the line. Now, if we multiply by t values bigger than 1, that's going to stretch the vector v in this direction. And if we multiply v by numbers less than -1, so like -2 for instance, that would stretch the vector in this direction to include this point. Now, if we allow t to range over all real numbers, negative infinity to infinity, this would effectively trace the full line. So that's sort of the idea behind a vector parameterization. So here's one copy of v, but this just continues onward forever.